Problem 1. The temperature of water in a tub at time t is modeled by a strictly increasing, twice differentiable function w, where Wt is measured in degrees Fahrenheit and t is measured in minutes. At time t equals 0, the temperature of the water is 55 degrees. The water is heated for 30 minutes, beginning at time t equals 0. Values of Wt at selected time t for the first 20 minutes are given in the table above.
Alright, use the data in the table to estimate W prime of 12. Show the computations that lead to your answer. Using correct units, interpret the meaning of your answer in the context of this problem.
Well, Bo, the answer to that question is a lot easier than you think. Let me show you how it's done. It's a simple average rate of change problem, as you can see. So, what's the question? At 12? 12 is in between 15 and 9, of course. So we're going to take f of b minus f of a over b minus a. In this case, I'll just show you guys that problem right here. Average rate of change. Can you see this?
Yeah.
So, you just go like this, f of 15 minus f of 9 over 15 minus 9. In this case, f of 15 is 67.9 and f of a equals 61.8. And then 15 minus 9, you guys can do that, 6. So the answer to that is 6.1 over 6. Simplify that, equals 61 over 60. And, Bo, that is your answer.
Units.
Don't forget your units, Bo, I almost forgot. And the units are degrees Fahrenheit over minutes.
Alright, Zach, B. Use the data in the table to evaluate the integral from 0 to 20 of w prime of t dt. Using correct units, interpret the meaning of this in the context of the problem.
Well, I'm going to need to ask my buddy Croix for this one.
Alright, so this is the integral from 0 to 20 of w prime t dt. And the way that the way this works is that the integral and the derivative cancel out. So then we use one of the fundamental theorems to take w of 20 minus w of 0, and that will give us our answer. So, so we have w of 20 minus w of 0. And then we go up to our chart above, which shows the values for w. And w of 20 is 71.0. Minus w of 0, which is 55.0. And that equals 16.0. And then we have to interpret the meaning of our answer in the context of this problem. And that's 16.0 degrees Fahrenheit, because we look up at the table, and w of t is in degrees Fahrenheit, so that's that. And then what that means is that from the integral of a derivative shows change over time, and so that shows the change in temperature in degrees Fahrenheit from t equals 0 to t equals 20. 16.0 degrees Fahrenheit, change in temperature from t equals 0 to t equals 20.
Alright, for C. For 0 is less than or equal to t, which is less than or equal to 20. The average temperature of the water in the tub is 1/20th integral from 0 to 20 w of t dt. Use the left Riemann sum with 4 subintervals indicated by the data in the table to approximate this. Does this approximation overestimate or underestimate the average temperature of the water over these 20 minutes? Explain your reasoning. Zach, I'll handle this. Since this is a left Riemann sum, we would use the furthest left on the table. So for the first value, it'll be this, using this number plus the difference between these two. plus the next one, since 4 and 9 is 5, times 57.1, and so on. All of this, since this is an average, is divided by the total value of 20. Plugging this into the calculator, you get 60.79 degrees Fahrenheit.
Oh, Bo, you forgot a huge step here. So, you have to explain whether this approximation overestimates or underestimates the average temperature over the 20 minutes. And it says up top that this is a strictly increasing graph. So that's like this. And then we split it into 4 different time zones.
Where did it say it's strictly increasing in
The first line is that. So a left Riemann sum means that we use the left point for each. So then for the first one it's just 0. The second one we take this point here, because that's the left point for this interval. So we draw that line over, and then the third one's there, fourth one's there. And so then that means that out of this whole graph, we only covered the blue stuff. We left this, and this, and this, and this open. So it underestimates the average temperature of the water over these 20 minutes. And that's true in all cases with a left Riemann sum, that for a strictly increasing graph, a left Riemann sum always underestimates.
Oh geez, thanks for saving me there, Croix.
No problem, Bo.
Alright, Zach, last part, D. For 20 is less than or equal to T, which is less than or equal to 25, function W that models the water temperature has first derivative given by W prime of T equals 0.4 square root of T cosine 0.06 T. Based on the model, what is the temperature of the water at time T equals 25?
Well, Croix seems to be on a roll, so I'll let him take this one over.
Alright, so for D, we have W prime T equals 0.4 times the square root of T cosine 0.06 T. And that's a rate. And so then to find the temperature at T equals 25, we take the temperature at T equals 20 and then find the total increase in temperature from 20 to 25 and then add that on to 20. So to find the total increase from 20 to 25, you have to take the integral of a derivative, because if you take the integral of a derivative, you find total change. So we have integral from 20 to 25 of W prime T dt. And W prime dt is 0.4 square root of T cosine 0.06 T. So then that means we have 20, 25, 0.4 square root of T cosine 0.06 T dt. And then we're just going to plug that into our calculator. And that, after we type that up in the calculator, that equals 2.043 degrees Fahrenheit. So that's the change in temperature from T equals 20 to T equals 25. But then it says they want to know what the temperature of the water is at time T equals 25. So at time T equals 20, that's the temperature at T equals 20 is 71.0 degrees Fahrenheit. And then we add the temperature from 20 to 25, so that's plus 2.043, and that equals 73.043 degrees Fahrenheit at T equals 25.
Good luck on your test, boys and girls.